Assalamu alaikum. I am SM Rohan Ahmed. My student ID is 2100211218 and my group partner is Ibteda210021211. His student ID is 2100211211. In this assignment, we evaluated Vienna 5G system level simulator. Using its predefined basic scenario, we first ran the original scenario with 5 MHz downlink bandwidth. Then we increased only the downlink bandwidth to 10 MHz and compared the result. Let's see the simulator overview section. The Vienna 5G system level simulator is a MATLAB based object oriented simulation tool developed by TUVM. It is used to investigate the performance of an entire mobile network containing base stations, sector, user mobility, propagation, interference, scheduling, etc. Whereas a link level simulator studies the detailed physical layer, performance one or small number of links, and a system level simulator studies the behavior of the complete network. The system level simulator uses link abstraction. The link quality model calculates SINR, while the link performance model uses the link quality to estimate transmission success and throughput. Now let's go to the MATLAB and see our system level 5G system level simulator. We downloaded the 5G system level simulator release 1.4 from online. Here everything are MATLAB files .m file. From here we choose our necessary files and used it for comparison for this assignment. The necessary file was the scenario file and the launcher file. Where is it? Here it is. Here the launcher simulation.m, we use this as an example, then modified it. As the simulator is provided as a MATLAB source code, the scenario definition are stored in the scenarios package. The executable launcher scripts are all inside the launcher files, and the main simulation procedure is implemented as simulate.m. This is that one. Now let's go to baseline time configuration. Let's search the chunk line. Here we got it. Here we can see the number of chunks are 10, the delay is 3, slots per chunk is 20, and time between chunk slot is 30. Let's understand this. The simulation uses 10 chunks and 20 slots per chunk, which contains 200 simulated slots. The feedback delay is 3 slot, only 3 slot. And the separation between independent chunk is 100 slot. The use of multiple chunks allowed the simulator to collect results from independent channel and network condition. Now let's see some other parameters. Yes. Here the downlink carrier frequency is set to 2 GHz. The original downlink bandwidth was 5 MHz, and later we changed it to 10 MHz for the comparison. Firstly, it was selected as 5 MHz, then we changed it to 10 MHz. Now let's search for some other things. Here it is. Here, the base station follow a two-dimensional Poisson distribution with a density of 10 base station per square kilometer. Here it is, 10 base station per square kilometers. Each base station contains 3 sectors and uses the predefined 3-sector antenna configuration. The number of transmit antennas is set to 1. Here the transmit antenna set to 1 and 3 sectors. Now let's see the user movement parameters. It's here. This block, random walk block, it defines the mobile users. The users also follow a two-dimensional Poisson distribution with a density of 20 users per square kilometer. Each user have one receive antenna, one antenna. The displayed random walk speed is 500 divided by 3.6, which is approximately 138.89 138.89 meters per second. Okay, a high speed is used. Here we used a high speed so that user movement can be clearly observed during the relatively short simulation. Indoor or outdoor status is decided using the geometry. The line of sight condition follows the urban macro 5G model, and the small scale fading channel, these are used. Now let's see the next code. The launcher example, which was given in the 5G system level simulator as an example. Here you can see RNG1 and this line, the result line. This point to the random number seed. This is the random number seed. This makes the generated network reproducible and helps us make a fair comparison between the two bandwidth cases, the 5 MHz and 10 MHz. Here in this line, the function params equal basic scenario, bandwidth 10 MHz. First it was 5 MHz, then we changed it to 10 MHz. This function receives the simulator parameter object as its input and returns the updated parameter object as output. It should not be executed directly because it requires the parameter object supplied by simulate.m. Running this scenario file directly produces some error. So let's go to the next part. Here you can see the parameters is 10 MHz. First we ran the code with 5 MHz, then we changed it to 10 MHz for the comparison. Now let's see the launcher example. The launcher also used a 10 MHz cell. It is important because the difference between two launcher commands is the scenario function handle. This launcher example uses the 5 MHz, and here we modified this code to 10 MHz. Here simulate.m is a 5 MHz code, and here in the basic scenario bandwidth 10 MHz we modified this code to 10 MHz. Now let's run this code. Here in the command window shows the simulation progress through chunks 1 to 10. Here you can see chunks 6, 7, 8, 9, 10 up to 10 chunks. During each chunk, the simulator loads the required fast-feeding channel traces and processes the corresponding slots. The simulation, the last line you can see simulation done, elapsed time 1.8 seconds and something. This confirms the baseline simulation completed successfully, and we got 4 figures. Here the simulation scenario figure, there are red circles, green symbols line, gray association lines, black movement arrows. You can see here large rectangular simulation area. Here it is, small central building, everything is here. It shows the network topology. The red circle represents the base station, this one, and this one the base station. The green symbols represents the user position. These are the users and their positions. The gray line, this gray line, they show the serving relationship between user to base station, the distance and everything. The larger rectangular boundary represent the simulation region, where the smaller rectangular near the center present the predefined building. This is the larger rectangular, and in the middle this is the smaller rectangular. Here other you can, in outside the rectangle you can see more red circles. These are also the base stations. Now let's move to the next figure. This figure represents the movement of the users. The green positions are the user's movement from here to here. This black arrow represents the users moving from here to here. Now let's go to the next figure. Users throughput. Here in the horizontal axis it is throughput megabit per second, and in the other axis it is ECDF, the vertical ECDF axis. ECDF means empirical cumulative distribution function, or in short user throughput. For example, the value of an ECDF level of 0.5 is the median. The value at 0.05 is the 5th percentile, and the value of 0.95 is the 95th percentile. The curve further to the right represent the higher throughput, this one, and the blue one is the feedback curve. Now let's move to the next figure. This figure also shows the ECDF, and in the horizontal axis it is the SINR in decibel. SINR compares the desired signal with noise only. SINR also includes interference from other transitions. Therefore, SINR curves are located considerably to the left here. This shows that the intercell interference has a strong effect on network parameters. Now, let's run the modified code. It is the same code, just the megahertz is changed from 5 to 10. The bandwidth is changed from 5 to 10 megahertz. Here everything you can see the chunks from 1 to 10. Here you can see the modified total runtime is 24.31 second, and the simulation is done. The elapsed time is here. Everything. We also got the four figures like before, just everything is changed because of the bandwidth change from 5 megahertz to 10 megahertz. We can see this everything in the report. Everything, all the parameters are given a screenshot here, and the explanation is written. I tried to incorporate every code explanation here and all the figure explanation here. Here you can see the red circles are base station, everything are explained here. The first launcher, it was for 5 megahertz. Again we changed it to 10 megahertz. It is also shown in the report. Then the launcher bandwidth, it was also changed to 10 megahertz, and it is known as modified launcher. Then the scheduling and association part, everything is inside a table and explained clearly. Here are the outputs and also their explanation. Here you can see the selected scenario is expected to generate four main graphical outputs. The first two was explained earlier, and here are the second two. The simulation scenario figure shows the location of the base station and the user, while the movement of a user figure shows the trajectory and direction of a selected user. The user light SINR, the left one, and the uplink SINR, the user throughput ECDF presents the distribution of DLFeedback and DLbestCQI. It is the channel quality level indicator. The saved performance figure are also to obtain from the fifth percentile. It was also explained earlier. For the code execution flow, I already explained it from the MATLAB, and here all the code snippet and their explanation is written. For the next part, the results and the discussion, it will be explained by my group partner Ibteda210021211. Thank you.
Now I will discuss the results obtained from our two simulated systems. We performed two cases. The first case used a 5 megahertz downlink bandwidth, which is our baseline case. The second case used 10 megahertz bandwidth. All the other major parameters, including the random seed network configuration, mobility, propagation model, and simulation during, were kept unchanged. Therefore, the main control variable in our experiment was the downlink bandwidth. Uh, Here at page 17, first let's look at the throughput result. For the DLFeedback throughput, the median value increased from 0.825 megabit per second with 5 megahertz to 1.825 megabit per second with 10 megahertz. This is approximately 121% increase. For DLbestCQI, the median throughput increased from 2.694 megabit per second to 5.311 megabit per second, which is approximately 97% increase. The median downlink SNR decreases from 69.302 dB to 66.329 dB, while the median uplink SNR decreases from 60.292 dB to 57.319 dB. So both decrease by approximately 2.973 dB. Here it's page 18. This is the comparison table. This table summarizes the comparison between the two cases. We can see that the throughput improvements are quite large, while the SINR changes are very small. The runtime also increases from 18.48 seconds to 23.400 seconds, which is approximately a 26.85% increase. This is the throughput graph. This figure gives us a visual representation of the throughput improvement. The 10 megahertz results are shifted toward higher throughput values compared with the 5 megahertz results. This happens because a larger bandwidth improves provides more frequency domain resources for transmitting data. Therefore, this scheduler has more resources available during each scheduling interval. Here we can see the SNR and SINR comparison more clearly. The SNR decreases by approximately 3 dB, but the SINR remains almost unchanged. This is important because SINR depends not only on noise but also interference and design signal power. Figure 6 shows the median SNR and SINR comparison. The decrease in SNR is clearly visible while the SINR value remains relatively close. Figure 7 shows the simulation runtime comparison. Now, based on discussion. Now I will discuss why these changes occur. The most important observation is the improvement in throughput. When the bandwidth increases from 5 megahertz to 10 megahertz, the system gets more frequency domain resources. This allows more data to be transmitted during each scheduling interval. That is why both DLFeedback and DLbestCQI throughput increase significantly. Now let's understand the SNR decrease. Thermal noise can be represented n equals to kdb, where b is the bandwidth. When the bandwidth is doubled from 5 megahertz to 10 megahertz, the integrated noise power approximately doubles. Doubling noise power corresponds to approximately 3 dB increase in noise power. Therefore, if the desired signal power remains approximately similar, the SNR decreases by about 3 dB. This is exactly what we observed in our simulation. The SNR decreased by approximately 2.973 dB. Another important factor is network geometry and propagation. The base station and user are endogenously distributed. Therefore, some users are close to their serving station, while others may be farther away or closer to interfering sectors. This case, different signal strengths, interference levels, SINR values, and throughput values. User mobility is also important. As the user moves its distance from the serving and interfering base station changes, this affects path loss, spreading desired signal power and interference. Therefore, the users do not experience one fixed SINR or throughput value. The simulator also uses its default scheduling and cell execution procedures. Execution determines which base station or sector serves as user, while scheduling determines which users and resources are selected during each slot. Therefore, although the throughput improvement is mainly associated with the larger bandwidth, its exact value is also affected by scheduling execution, interference and link adaptation. Finally, the simulation runtime increased from approximately 18.400 seconds to 23.400 seconds. The larger bandwidth may require additional processing of frequency domain research and scheduling information. To summarize our findings, the median DLFeedback throughput increased from 0.825 to 1.825 megabit per second, and the median DLbestCQI throughput increased from 2.694 to 5.311 megabit per second. At the same time, both uplink and downlink SNR decreased by approximately 3 dB, while SINR changed only slightly. So overall, increasing the downlink bandwidth from 5 megas to 10 megas substantially improves downlink throughput. However, this improvement comes with an approximately 3 dB reduction in SNR and moderate increase in simulation time. Therefore, our experiment demonstrates that increasing bandwidth is effective for improving throughput, but its performance should always be considered together with the other factors affecting a wireless network. Thank you.